In this video, we will be looking at piecewise functions. First of all, a piecewise function is a function that is made up of multiple pieces, multiple segments, or multiple functions. So in this first example, you will see the following function that has been called f at x, and it is made up of a line, a parabola, a cubic, and a horizontal line. We're going to start off by finding the equation of this piecewise function, which means we're going to have to find 4 separate equations and then state the domain for each piece. So I'm going to start off with the line. With the line, we know that the form is going to be in y equals mx plus b. Our slope, we can read off very clearly from the graph. We can see that the slope is negative because the line is going down, and we're going down 1 to the right 1, which means the slope would be -1. Now for your y-intercept, we can just continue our line and see where it would cross. So if I were to continue, it looks like my y-intercept would go to -3. Now I could also solve for my y-intercept if I wanted to, using my grade 9 skills of finding the equation of the line. I can plug in my slope into my equation and say y equals -1x plus b, and then pick any point on the line and sub it in for x and y. For example, if I wanted to pick -3, 0, I could write 0 equals -1 times -3 plus b. -1 times 3 is +3, and when that moves over, we get the exact same -3 y-intercept. So now I'm going to write it for my piecewise function. I'm going to start with f at x equals, and then this giant squiggly bracket, and we're going to state the first equation, which is -x or -1x subtract 3, and then we're going to write our domain for this line. Now this line has x values between -5 and -2, and these values are included because they're closed points. So I'm going to write for x belongs to -5 to -2. So I am using interval notation here, and I'm just stating that it's the x values that I'm giving this interval for. And that's it for the line. Now we can go to our parabola, and we can write our parabola equation in vertex form. We see our vertex is at 0, 3, which means there is no right-left movement, but we are moving up 3. Now, I also notice that there is a reflection over the x-axis since this parabola is opening down. I also notice that the a value should be -1. Negative because of the reflection, and 1 because this hasn't been stretched or compressed, and I can tell that from the step pattern. From this vertex, I go to the left 1, down 1, left 1, down 3. And the original step pattern is 1, 3, 5, which we saw back in grade 10. So I can go straight to my equation. However, if I couldn't see that a value, I will do a little refresher on how to find that a value. So I'll start with y equals a, and then there is no right-left movement, so I'm just going to go straight to x squared. If there had been right-left movement, I would open a bracket, write x plus or minus that value, and then raise it to the power of 2, and then plus 3. Now again, I'm going to pick a random point that I can read on my parabola. I'm going to choose to use -1, 2. I cannot use the vertex again, or else my a will disappear. So 2 for y, -1 for x, Now I'm going to clean up. I'm going to bring the 3 over to the other side. So 2 minus 3 is -1. And then -1 all squared is +1. And there's that a value that I was able to read off, but I can also solve for it. And now I'm going to write -x² plus 3. And this is for the interval x belongs to, we start at -2 and it's a closed point, so a square bracket, and we go to x being +1 where there is a hole, so I'm going to have a curved bracket there. Next, we have our cubic function here. Okay, now I'm going to use this point for my shift values. This point used to be at the origin. It must have moved to the right 2 and down 1, which means right now my equation would be y equals a x minus 2 cubed, because it's going to the right 2, and then -1 for the down 1. Now this a value, I can see it from this point here. On the base function, there would be a point right here, just 1 unit away, left and up, but it's 2 away, so I do know that there's a vertical stretch by a factor of 2. I also know that this has been reflected over the x-axis because the original cubic function has an overall upwards trend. So I can visualize my a value, but I can also find it algebraically. This time, I'm going to plug in this endpoint at 1, 1 and solve for a, just like we did last year, or grade 10 for parabolas. So I'm going to bring the -1 over, it becomes positive. Simplify that bracket, so we actually have -1 cubed. -1 cubed is just -1. And when you divide both sides by -1, there's that -2 a value. So our cubic equation is -2 x minus 2 cubed minus 1, and that's from the x values of 1 to 3, including them, because those are closed points. And our final equation is this horizontal line. A horizontal line always has the equation y equals the value. And if we look at this horizontal line, if we were to extend it backwards, it's at 2. All of the y values on this line are 2. 5, 2, 6, 2, and so on. So this equation is just 2 for x belonging to the interval 4 to infinity. And that's how we find the equation of a piecewise function. We're just using our prior knowledge of finding equations, whether it's for lines, parabolas, cubic, horizontal lines. We could have square roots on here, we can have sinusoidals, rational, exponential, any of those base functions we have seen in the past. We know how to find the equation of all of them. Sometimes we can just look at the equation, figure out our shifts, even figure out our a value, but when we can't find a piece of the equation, we can always sub a point in and then solve for that a value. Now that we have our equation, we can answer some questions about properties or points on this graph. So I'm going to start off with finding f at -4. This means we're given the x value and we're looking for the y. So if I look at x being -4, y is +1. F at 0, I'm looking at x equals 0, and I see my parabola is at 3 for the y. So f at 0 equals 3. F at 1, when I look at x equals 1, I have a closed point and a hole. The hole doesn't actually exist, so this is the point we're considering. When x is 1, y is also 1. For f at x equals 2, this is now our y value, and we're looking for the x. So I'm just going to highlight this 2 value because there are quite a few options for x. We have x equals -5 when y is 2. We have x equals -1. And we have the whole horizontal line. So I'm going to write that x belongs to 4 to infinity. So we actually have an infinite number of options when f at x equals 2. Next, we are asked about our maximum value. The only arrow I see is for this horizontal line. None of the other segments go up or down forever. So my highest possible value is here. It's a maximum of 3, and we are looking at the y value. And my lowest value is here at the cubic at -3. Next, we have our domain and range. So for my domain, -5 is the smallest value. I follow the line, the parabola. Even though I have a hole here, I hop onto the cubic and I end at 3 for that first continuous segment of x's, because after that I have empty space between 3 and 4. So my domain is from -5 to 3, and then for the horizontal line, 4 to infinity, but 4 is not included. For my range, my lowest is -3, my highest is +3, so our range is just -3 to 3. All right, next we have our intervals of increase and decrease. So I'm just going to highlight increase and decrease. So from -5 to -2, we are decreasing. Then when we get on our parabola, we increase until we hit that vertex. Then we decrease. Then we jump onto the cubic and decrease. But keep in mind that on the cubic function, at that point of inflection, there is no increase decrease, so we will have to separate those. And then when I hop onto the horizontal line, that's not an increase or decrease segment. That's actually its own thing, which is an interval of constant. And that is a new property we're going to have for this piecewise function. So let's write these out. My interval of increase is only that little segment of the parabola that is climbing from left to right, which is from -2 to 0. We're stating the x values where we are increasing. For intervals of decrease, I have quite a few. We start from -5 to -2 when we're on that downwards line. Then we're from 0 to 1 for the rest of the parabola. Then for the cubic function, we go from 1 to 2, then we hit the point of inflection, then we go from 2 to 3. And then for our interval of constant, we're constant from 4 to infinity. If that point at 4, 2 had been a closed point, then I would use a square bracket here, but it was open, so I put a round bracket. Next, we have our positive and negative intervals, which I am going to hold off on doing until I find my x-intercept. So I'm going to jump to my intercepts. I'm going to have to do some calculations, and then I'll be able to state my other intervals accurately. I'm going to start with my y-intercept, which I can see clearly right here on the parabola. It is at 0, 3. If I couldn't read it properly, I would have to see, okay, I'm on the parabola, which means I would set the parabola equation equal to 0, the x value, and then simplify it to get the y. Now for my x-intercepts, I see there's an x-intercept on the line that I can clearly read off. It's at -3, 0. If I couldn't read it off, I would go to my line equation and set it equal to 0 and solve for x. So for example, just in case, here's what I would do to solve for it. And it's a quick solve. In this case, there's that first x-intercept. On the parabola, I have an x-intercept that is not exact. So I'm going to set my parabola equation equal to 0, and I'm going to isolate for x. So I'm going to bring the negative x squared to the left to turn it positive, and then I have to square root both sides. And when I square root both sides, it's going to be plus or minus 3. Now, if I look at the actual parabola, the positive value, so the positive square root of 3, would be outside of the domain boundaries because my boundaries are from -2 to 1, whereas the square root of 3 is 1 point something. It would be somewhere here. So that one we're going to disregard, and the only one that's going to count for us is the negative square root of 3, 0. Our final x-intercept is on the cubic function, which is again not an exact value. So I'm going to set my cubic function equal to 0. And now I'm going to isolate for x. So bring the -1 over, it turns positive, divide out the -2, so we have -1/2. To get rid of the cube, we're going to cube root both sides, which will make the cube cancel out on the left, and we'll have the cube root of -1/2 on the right. As a reminder, when you take the cube root or any odd root, you will not have the plus or minus like you would for an even root. Also, we are allowed to cube root a negative number because a negative to the power of 3 will give us a negative value. And finally, if we bring the -2 over to the other side, here we have our exact x-intercept. Now, if you look at this value, it doesn't look like it's the nicest number. If you're unsure of it, you can always punch it into your calculator and see if you get approximately 1 point something, which is what we would have predicted. And when I plug this value in, I get approximately 1.2. It makes sense. So I do feel confident about this value. And now that I have my x-intercepts, I can state accurate positive and negative intervals. And again, I'm going to highlight them. This is my first positive interval from -5 to -3. Then I have this interval here from the -√3 x-intercept until 1. And then from 1 to the other x-intercept. And this horizontal line will be positive. For my negative, I only have the -3 to -2 and the rest of the cubic function. So let's write our intervals. My first positive one is from -5 to -3. Because at -5, the coordinate is -5, 2. 2 is actually a positive number. I put a square bracket on -5 because it has a positive value. -3 was an x-intercept. Its y value is 0, so it had the round bracket. Next, for the parabola, we're going from -√3 until, and here we can actually combine the parabola and that little segment of the cubic function, because at 1, although there's no positive value on the parabola, it exists on the cubic function. So we can just state from -√3 to the cube root of -1/2 plus 2. And then for that horizontal line, we're just going from 4 to infinity for a positive interval. And our negative interval, we have -3 to -2, and then from that cubic x-intercept to 3. And at 3, the coordinate is 3, -3. The y value is actually negative, not an x-intercept, so I'm putting a square bracket. And finally, our end behaviors. As x approaches infinity, y approaches, well, it doesn't go up or down to infinity, it just stays at 2. so y is approaching 2. And as x approaches negative infinity, y does not exist because on the left side, we don't have more going on. Everything stops at negative 5. So there's our first very full example. Let's move on to another example. So in this next example, we have a piecewise function made up of a line, a horizontal line, and then this would appear to be a square root. So we're going to start off with the equation and then the properties. And this is called f at x, so I'll write f at x equals, I'll open up my giant bracket to fit my 3 equations. For my first line, the slope is once again down 1 to the right 1. It's a negative slope, so negative x, and the y-intercept we can clearly see is the origin, so just negative x. Technically negative x plus 0, but unnecessary. And that's for x belonging to negative infinity all the way to 0, 0 included. For the horizontal line, the equation would be just y equals negative 2, because all the y values there are negative 2. And that's for x belonging to 0, not included because it's a whole, all the way to 4, which is included because it's a closed point. And then for the square root function, this point here used to be at the origin, so it must have moved to the right 4, and it did not move up or down at all. I see that there's no reflection because the original base function would have had that same shape. And the original base function would have had 0, 0, and then a point at 1, 1. This is 0, 0 transformed, and this is the 1, 1. There is no stretch compression. So I know my a value would be 1. If I wanted to solve for it, I could, like I did in the previous example. But I'm just going to go straight to the square root of x minus 4, because it went to the right 4, for x belonging to 4 to infinity. 4 is a round bracket because it's a hole there. Now let's state some properties. The zeros, there's only one, and it's at the origin. It's exact, we don't need to solve for it. The y-intercept is also at the origin. F at 4, so when x is 4, what is y? Well, at this one, it's a non-existent point. And this is the one we're looking at, y is negative 2. F at x equals 5. So now I'm looking at my y value being 5, and I look across, and here it is, x equals negative 5. That being said, we do have to look at the big picture here. It looks like it's just the line that has that point, but this square root will continue, and eventually it will be at 5. So there is another point, and we should probably solve for it because the graph will not show it to us. So I'm going to set the square root of x minus 4 equal to 5 and isolate for x using my algebra skills. I'm going to start off by raising both sides to the power of 2, and that's going to give me x minus 4 equals 25. Bring that 4 over, it becomes 25 plus 4, which is 29. So when x is 29, y will also be 5, and we had to solve for that. Next we have our domain and range. So we know that this is going forever to negative infinity for our x's. Once we hit x equals 0, we hop on the horizontal line. From here we hop on the square root function. So our domain is from negative infinity to infinity. For our range, y can be negative 2 because of that line, and then everything above 0. So we can write y equals negative 2, and then 0 to infinity. And you can, of course, also use set notation here and write y is an element of all real numbers, y equals -2, comma, y is greater than or equal to 0. If it's not specified that you have to use interval notation for your domain and range, you can use set notation. But for the rest of the properties, of course, interval notation. All right, intervals of increase. My only interval of increase is on the square root. This is the only one that's increasing. This line is decreasing, this line is constant, this one is increasing. So my interval of increase is from 4 to infinity. My interval of decrease is from -infinity to 0. My interval of constant is from 0 to 4. And at 4, I was able to put a closed bracket because that is an actual point, and that entire line segment is horizontal. It's constant y values. They are not going up or down like on the downwards line or the square root. My positive interval is this line segment and the square root. So that would be from -infinity to 0 and from 4 to infinity. My negative interval is that horizontal line segment that is from 0 to 4. At 0, I put a round bracket because that point is not actually -2, it doesn't exist. And at 4, I put a square bracket because at 4, the y value is actually a negative value. The maximum of this function does not exist because these parts go up forever. There is no maximum, but the minimum would be this -2 where that horizontal line is. And our final example, our piecewise function here is made up of an absolute function, a parabola, and a horizontal line. So let's start off with the equations. F at x equals, for the square root function, I know that it must have moved to the left 3 and down 4 for the point that used to be at the origin to be here now. I can also tell that the a value is 1 because the next point is just 1 over, like the original. There is nothing that has stretched it to make it look steeper. But you, of course, can solve for the a value like we did in the previous examples. I'm going to go straight to my equation and write the absolute value of x plus 3, because we're going left 3, and minus 4 for x belongs to -infinity to -2, which we're including. Now, if I wanted to solve for my a value, I'd write my a value right here, plug in a point for x and y, and solve for it, just like we did last year. For the parabola, I do notice again my step pattern is 1, 3, so I know the a value is 1, but because of the reflection over the x-axis, it's -1. So negative. And then there is no right-left movement because the vertex is on the y-axis, so -x squared and then plus 3, just like the other example. And that's going to be for x belonging to -2 to +2. +2 was a closed point. And finally, for that horizontal line, y is just equal to -1 there, so -1 for x belonging to 2 to infinity. And those are our equations. Many times you don't need to solve for an a value if you're super familiar with the base function and notice what the next point is. But again, it is an option you can use if you need to solve for a, if you're unsure of yourself. All right, zeros and y-intercepts. I'm just going to write my y-intercept first because I can clearly see it at 0, 3 on the parabola. For my zeros, however, I know I'm going to have 2 from my parabola, so I actually have to solve for it. like we did in the first example. And although I don't see it, I do know that this absolute value function will go to an x-intercept, which, I mean, I can extend this and realize it's just going to be at -7. But in case that didn't happen, I will solve for it as well. So I'll show my zeros down here. I'll start with my parabola. So just setting -x² plus 3 equal to 0. I'm going to bring the x² over because I'd rather it be positive, and then square root both sides, and we get plus or minus the square root of 3. So root 3 comma 0, negative root 3 comma 0, and now we just need that absolute 1. So I'll take my absolute equation and set it equal to 0. I'll bring the 4 over. And now let's remember what absolute value signs do. They take whatever's in the bracket and turn it positive. So that means if the value inside the absolute value signs was 4, it would turn 4. If it were -4, that -4 would turn into its absolute version, which is +4. So I have to write two versions here. X plus 3 can equal 4, but x plus 3 can also equal -4. And then I bring the 3 over. So 1 or -7, because that 3 turns negative. And now let's just go back to what this means. If x were -7, -7 plus 3 is -4. And then these absolute value signs would turn that -4 into +4. That's what the signs do, and that's why we have two options. Now I have two options, but which one makes sense? X equals 1 is out of the domain because our domain is from -infinity to -2. So this one will not make sense for us. But -7 comma 0 is great for our third 0. Next, f at -2. So when x is -2, not the whole, it's going to be the point on the absolute, which is -3. F at x equals -1. Here's -1. I have a point on the absolute value where x equals -6. And x also belongs to 2 to infinity. Next, for our domain, it is once again -infinity to infinity because there are no breaks in the x values. And for our range, we are from -4 to +infinity. Even though it looks like the parabola ends there, you have to remember that the absolute value does go on forever. So we are from, just going to write it here, from -4 included all the way to infinity. Next, intervals of increase. I am going to highlight here. This first part of the absolute value decreases. Then it increases. Then we switch gears and we increase on the parabola. Then we decrease. And then we have a constant segment. So my increase is just that tiny portion on the absolute from -3 to -2, and then from -2 to 0 on the parabola. The interval of decrease is from -infinity to -3, and then from 0 to 2. And the interval of constant is from 2 to infinity. And again, at 2, it's a closed point. It's a constant value. I'm including it there. All right, positive interval. Remember, you have to look at the big picture. That absolute value function, when it hits -7, it goes forever. So there will be a portion that is in the positive region. And it's going to be from -infinity to that x-intercept of -7. And then we're positive between the two x-intercepts of the parabola. So that's from negative root 3 to positive root 3. And that's it for our positives. Our negative is going to be from negative 7 to negative root 3. So that's this portion of the absolute and this little portion of the parabola. And then we're negative from positive root 3 forever. Maximum we don't have, okay? Don't let the parabola trick you. The absolute value sign is going forever. So it does not exist. And our minimum would be that little vertex of the absolute value. So we have a minimum of negative 4. So with piecewise functions, you need to pretty much bring all of your algebra and graphing skills together. So finding the equation of the separate individual pieces using your prior knowledge of base functions, shifts, a values, y equals mx plus b. And then you have your properties, which you have to read the graph carefully for. And of course, you need good algebra skills when you're solving for that x-intercept or multiple x-intercepts. And that's it.